Introduction to Statistics, Chapter 5, Probability, Section 5.1, Probability Rules. Probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. Law of large numbers. As the number of repetitions of a probability experiment increase, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. In probability, an experiment is any process with uncertain results that can be repeated. The results of any single trial of an experiment is known ahead of time. It's not known ahead when you run the experiment. However, the results of the experiment over many trials produce regular patterns that allow accurate predictions. The sample space S of a probability experiment is the collection of all possible outcomes. Examples. If your probability experiment consisted of rolling a die, your sample space would be S equals the set of 1, 2, 3, 4, 5, 6. These are the outcomes possible when you roll a die. 2. If your probability experiment consisted of tossing a coin, your sample space would be S equal to the set of heads, tails. When you toss a coin, you only have two outcomes, heads or tails. 3. If your probability experiment consisted of birth of a child, your sample space would be S equal to the set of boy, girl. Okay, whenever a child is born, it's either going to be a boy or it's going to be a girl. Two outcomes possible. A simple event, E sub I, is a single outcome of a probability experiment. An event, E, is any collection of outcomes from a probability experiment. An event consists of one outcome or more than one outcome. An example, if your probability experiment was to draw a card from a set of 4 cards numbered 1 through 4, your simple events could be E1 could be draw the card with a 1 on it. E sub 2 could be draw the card with a 2 on it. E sub 3 could be draw the card with a 3 on it. E sub 4 could be draw the card with a 4 on it. Your sample space would be S equal to the set of E1, E2, E3, E4, or the set of 1, 2, 3, 4. A possible event might be E equal to E sub 1, E sub 2, E sub 4, or the set of 1, 2, 4. Another possible event might be equal to E sub 4, which is just the set of 4. Rules of probability. The probability of any event, E, denoted P with E in parentheses, must be greater than or equal to 0 and less than or equal to 1. That is, probability of E is greater than or equal to 0, less than or equal to 1 in algebraic terms. 2. The sum of the probabilities of all outcomes must equal 1. That is, if S, your sample space, equals E sub 1, E sub 2, all the way down to E sub n, then the probability of E1 plus the probability of E2 plus all the way down to the probability of E sub n has to equal 1. 3. If an event is impossible, the probability of the event is 0. If the event cannot happen, it's going to have a probability of 0. If an event is certainty, the probability of the event is 1. If it's certain to happen, guaranteed to happen, your probability is 1. 5. The closer a probability is to 0, the less likely the event will occur. 6. The closer a probability is to 1, the more likely the event will occur. 7. An unusual event is an event that has a low probability of occurring. Typically, an event with a probability less than 0.05 or 5% is considered unusual, but this cutoff is not set in stone. Some people use a 1% cutoff. Some people use a 10% cutoff for unusual events. So it depends upon what you're measuring and how accurate you want to be. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probability. Example: is the following probability experiment a probability model? If we look at it, X is colors: red, white, blue, black, green, purple. The probability of X is 0.11, 0.26, all the way down to 0.04. So if I want to see if this is a probability model, first I'm going to check rule 1. Are all probabilities between 0 and 1 inclusive? And in this case they are. So yes. Second, check rule 2. Is the sum of the probabilities equal to 1? So I take the probability of X, 0.11, 0. Add them all up, and in this case, yes, they do add up to 1. Hence, this is a probability model. Looking at example 2. In this probability model, first, check rule 1. Are all probabilities between 0 and 1 inclusive? Well, no. Probability of blue is less than 0. It's negative 0.18. Hence, this is not a probability model. Example 3. What about this one? Check rule 1 first. Are all probabilities between 0 and 1? If we look down through, yes, they are between 0 and 1. Second, check rule 2. Is the sum of the probabilities equal to 1? So I go through, add all the probabilities, 0.11, 0.25, all the way down to 0.04, add them up, and in this case, no. That sum is equal to 0.98, so it does not equal 1. Hence, this is not a probability model. Approximating probabilities using the empirical method. The probability of event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. Okay, if we think back to earlier chapters, this is the same thing as relative frequency. So the probability of E is approximately the relative frequency of E, which is equal to the frequency of E divided by the number of trials of the experiment. This is sometimes referred to as experimental probability. Example: given the following frequency distribution for M&Ms in a bag, build a probability model using the empirical method. Well, this is a frequency distribution. So I'm going to have to create a probability model. So I need X is going to be the colors: red, green, blue, brown, yellow, orange. Now instead of frequency, I want the probability that I'm going to get a red, probability I'm going to get a green in the bag. So first thing I have to do is find the sum of the frequencies. If I add up the frequencies, I get the sum of the frequencies to equal 40. Now I have to take each frequency and divide it by the total of the frequencies. So 10 divided by 40 is 0.25. So probability of a red is 0.25. 0, I usually use 3 decimal places, but you do not have to. Next, green. There's 5 green, so 5 divided by 40 is 0.125. So we have 0.125. Blue, there were 7. 7 divided by 40 is 0.175. And we go down through. Take 8 divided by 40, 0.200. 6 divided by 40, 0.150. 4 divided by 40, 0.100. And if you added all these probabilities up, you should get a sum of 1. Now, example, if you choose 3 cards from a set of 5 cards with the names Matt, Sue, Ann, Bill, and Joe written on the cards respectively, what are the different possible outcomes when you pick 3 cards? Well, first, let's look at the sample space. The sample space would be Matt, Sue, Ann, Bill, Joe. These are the names we can draw. Now, I want all outcomes of 3. So I'm going to take Matt, Sue, Ann first. You notice I took the very first 3. Then I'm going to take Matt, Sue, Bill. Then I'm going to do Matt, Sue, Joe. You see the pattern I'm starting to build for getting my groups of 3. Next, I have everything with Matt, Sue as the first 2. So now I'm going to go Matt, Ann. Matt, Ann, Bill. Matt, Ann, Joe. Now that takes care of Ann as the second. Now I go with Bill as second. Matt, Bill, Joe. So that takes all the possibilities with Matt being the first person chosen. Now I'm going to take Sue as the first person. So I could have Sue, Ann, Bill, Sue Ann Joe, Sue Bill Joe. Okay, and that's it with Sue as the first. Now I go with Ann Bill Joe, and that's the only one. And I never go backwards. I always go to the right. So I'm done. So there are 10 total possible outcomes for picks of these 3 cards. Now, B, compute the probability that Matt, Bill, and Joe are chosen. Well, I look at my outcomes. There were 10 possible outcomes up above. So which one has Matt, Bill, and Joe in? Well, that would be 1 right there. So there's only 1 out of the 10. So the probability that Matt, Bill, and Joe are chosen is 1 out of 10, or 0.100. C, compute the probability that Matt and Ann are chosen. Now, this time I want 2 people chosen, but remember there's groups of 3. So I have to look at every group of 3 that has Matt and Ann in it. So the first group has Matt and Ann in. If I move over, Matt, Ann. And I don't see any other groups with Matt, Ann in, so this is a total of 3 out of the 10, or 0.300. D, compute the probability that Sue is chosen. Okay, so in this case, I'm going to look for any group of 3 that has Sue in. So here's Sue, 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 Sue. So it turns out there are 6 of the groups of 3 that have Sue, so the probability is 6 out of 10, or 0.600. Now, we want to talk about the classical approach, or classical method. Okay, if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E, again signified P with E in parentheses, is. The probability of E is the number of ways that E can occur divided by the number of possible outcomes. And up in the definition, I let m be the number of ways E could occur and n be the number of possible outcomes. That's where I got the m over n. Okay, if S is the sample space of an experiment, we could also do n of E is the number of outcomes in E, and n of S is the number of outcomes in the sample space. Then the probability of E would be n of E divided by n of S. This is just another way to write the same formula, different notation. This is sometimes referred to as a theoretical probability. An example, given the sample space S equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and suppose the outcomes are equally likely. Okay, excuse me. Compute the probability of event E equal to the set of 1, 2, 3. Well, if I look at the set of 1, 2, 3, there are 3 elements, outcomes, and the sample space has 10. So this is 3 out of 10, or 0.3. B, compute the probability of event E. If I look at E, there are 1, 2, 3, 4 outcomes in E, and there are 10 in S, sample space. So this is 4 out of 10, 0.4. If I said compute the probability of event E, which was a set of 2, 4, 6, 8, 10, there are 5 outcomes in E, so this is going to be 5 out of 10, or 0.5. Now, subjective probability. The subjective probability of an outcome is the probability obtained on the basis of a personal judgment. For example, the probability that George will arrive on time to go to the movies. No records have been kept, so you just make an estimate based on your knowledge of George arriving on time. You may have one of these friends. You know, some friends are always on time, some friends are always 10 minutes late, some friends, are on time and they're late. It varies, so you have to make a judgment. So in this case, you just, your knowledge of George arriving on time. So you estimate probability on time 40%, or 0.4 or 2/5 from the past experience. Now remember, probability may be written as a percentage, may be written as a decimal, may be written as a fraction. So read the questions carefully. See which way they want it. Okay, this is the end of section 5.1.